Hello, good morning. So, let's start the class now. We still have 1 minute, but yeah, let's start anyway. So today's class will be a rather short one. We will finish our discussion on Markov chains, and then with this example, this is a very interesting example called Parrondo's paradox. Okay, let me make sure that can you hear my voice clearly? So, so just make sure that everything is okay. Oh, okay. So yeah. Thanks. Okay, thanks. Okay, so let me continue. Mm. Okay, so this example has a lot of, similarity with the two-set problem and the gambler's ruin problem that we have seen. So we will look at it. So this is a problem that is invented by a physicist called Juan Parrondo. And then we will see that in this example, we will have two games that are played on a die, no, a coin. But then each of the game is not a good one if we play for the in the long run. But on the other hand, if somehow we will randomly pick a game to play each time, and then we play in the long run, then interestingly, it may become a better game for us. So let's see what it means. Okay, so let's consider this example first. So we call this game A. Game A, we have a biased coin, and this coin comes up with head with probability 0.49, and then tail with probability 0.51. And then for us, we will win $1 if head comes up, and then we will lose $1 otherwise. So in this case, we will see that the case that we're winning is only 0.49, so it is less than half. This is not going to be a good game for us. So if we want to play this game A forever or for a long run, then we are going to lose money. So we should not be playing this game A again and again and again. And then next, let's see the second game. So this, let us call it game B. Now game B is a bit complicated. And so for this game, we are having two biased coin. So it depends on the current money that we have. We will choose the two different biased coin to play. Okay, so here, so our initial money, let's say our initial money is $0. Okay, and then we are going to only to play this game. So we will be winning $1 or losing $1 each time. And then the first coin here is when our money currency is not a multiple of 3. So if it is the case, then we are having more chance of winning, 0.74 chance of winning, and then we have less chance of losing, 0.26 only. So it is the same as the first game here. When head comes up, we are going to win $1, and then if tail comes up, we are going to lose $1. So this is the case when our current money is not a multiple of 3. But on the other hand, if our money is a multiple of 3, then we will be using the other biased coin. So in this case, we are going to win only with 0.09 chance, but then lose most of the time. So we will be losing with 0.91 chance. Okay, now suppose that we can play this game B again and again and again. So, so let's say we have $0 initially. So we are going to use this second coin, and then we flip this coin, and somehow let's say head comes up so that we win $1. And then in that case, we are going to use the first coin, and then if head comes up, we will be winning $1, so that we will now have $2. And then after that, maybe tail comes up, then we will be having $1 back, and so on and so forth. So this is game B. If we want, so if somebody wants to play game B with us in the long run, should we accept the offer? Now to analyze this, okay, so to analyze this, we will see that all depends on multiple of 3. So what we want to analyze this is, if we start with $0, is it more likely that we will win $3, or is it more likely that we will be we will lose $3. Which is more likely to occur? If we have more chance of winning $3, then we should play this game, because after that we are going to have another multiple of 3, and then there is more likely to win $3, so that we will be gaining $6, and then we will have more chance to gain $3 again, so we'll be having more chance to get to $9, and so on and so forth. So in that case, the critical part here is we want to analyze whether it is more likely for us to win $3 before we lose $3. Okay, so this is easy. We can use the Markov chain to help us to do the analysis. So we don't need to consider the infinite long Markov chain, because we just need to focus whether, so initial money is 0. We want to focus whether we are winning $3 more likely or we are losing $3 more likely. So in that case, this Markov chain only have finite number of states, and then and then here we have the transition probabilities based on the bias coin we are using. So this P12 means that we are using the first coin, and then when it is not a multiple of 3, so what is the chance that we are going to gain $1? So if this is going up with P12, then it will be going down with 1 minus P12. So similarly, if we are in this case, when we are having $2 in our pocket, then in that case, we will go forward with P12, and then we will go backward with 1 minus P12. So similar for -1 and -2. So go forward with P12, because these two states represent that we are not having a multiple of 3 as our money. And then for these two states, we go back with 1 minus P12. The only exception is this one. This is the state where we have exactly a multiple of $3. So we will go forward with a certain probability P3 here, and then go back with 1 minus P3. And then this game will stay. So because we want to find out which probability, whether this one is more likely to occur or this one is more likely to occur, then we will stay that, we will stay here forever if we reach this state, and also we will stay here forever if we reach this state. Okay, so if you realize this figure, it is actually the same as we are analyzing the gambler's ruin Markov chain, except that during the time that we are analyzing the gambler's ruin, then the probability in between, they are all 0.5, and here it is not. Okay, but then we have the same idea of solving the problem, because all these P12, P3, and 1 here, these are known values. So what we want to do here is that let us define Z of J to be the chance that we will win $3 before losing $3 when we start at state J. So we can define what is Z0, Z1, Z2, Z3, Z-1, Z-2, and Z-3. So we are going to have 7 variables that we want to determine. And then we have Z-3. If we already have lost $3, then there is no chance of winning $3 before losing $3. So in that case, Z-3 will be equal to 0, and Z3 is equal to 1. Is that okay? So we will have these constraints. We are certain. Now for the other, so it is actually computed based on the weighted probability. So for instance, Z0. So what is the chance that if we start at state 0, we will be winning $3 before we lose $3? Okay, we will see that first of all, there is P3 chance that we will move forward. So when we move forward, after that, there will be Z1 chance of winning $3 before losing. And then there is 1 minus P3 chance to move backward. And then if we move backward, then there will be Z-1 chance to further to win $3 before we lose. So that means that we can establish an equation for Z0. Okay, based on this weighted probability formula. And then we can do so for Z-2, Z-1, and so on and so forth. So in that case, we have actually 7 unknowns, and then we have also 7 equations. Okay, And then actually there's an extra equation. So here, actually these equations, they are somehow dependent a little bit. So indeed, we have the eighth equation that says the sum of the probabilities z minus 3, z minus 2, z minus 1, z 0 up to z3. Oh, no. We just have these 7 formulas, sorry. We have 7 equations, 7 unknowns. So in that case, we can solve it. And then in particular, we can find that z0 can be represented based on the known values p3, p12 in this way. Okay, so let's trust this is correct. Okay, and so for our particular scenario, we can find out whether using the dice, the coins in our game B, whether we are going to have z0 to be greater than 0.5 or less than 0.5. Okay, so we are now going to plug in the value of P3 and P12 into this formula and see what will happen. So in our case, P12 is 0.74 and P3 is 0.09. So after plugging it into this formula, we will find that Z0 is actually smaller than 0.5. So if we start at state 0, the chance that we will win $3 before we lose is less than 0.5. So in that case, game B is not a good game for us to play in the long run. Okay, now what Parrondo's invented is the game called Game A plus Game B. Let's call it Game C. So how are we going to play this Game C? Game C is interesting. So each time we are going to first flip a fair coin. Okay. When we flip this fair coin, we decide whether in this round, whether we are going to play Game A or Game B. So we are going to play Game A or Game B for one round. That means that after this round, we will be either winning $1 or losing $1. After this round, we are going to flip a fair coin again to decide whether we are going to play Game A or Game B. And in that case, we will either win $1 or lose $1. Is that okay? So Game A and Game B, the rules are still the same. Okay. So Game A is independent of the money that we have. We are always having 0.49 chance of winning $1, 0.51 chance of losing $1. But for Game B, it really depends on the current money that we have. Okay, so if we are, let's say if we have $3 and somehow we flip a fair coin to decide that we are going to play Game B in this round, then we will follow the rule of using the corresponding coin of Game B in this round. Okay? So in that case, so this gives us the Game C. So the intuition here is whether Game C is good for us. The intuition here, it looks like because we have roughly 50% of the chance that we are playing Game A and 50% of a chance of playing Game B, and then these two games are bad for us in the long run. So we have half of a chance of choosing the first bad game, and then half of a chance of choosing another bad game. So that means that it looks like in the long run, we are going to be bad. But then this is counterintuitive. So this is why this is an interesting problem. It turns out that, okay, under special conditions, the value of P12 and P3 that we have, really, Game C may not be that bad. So let's see what will happen if we are doing something like this. So now, so we have the setting. We have already defined what is Game A and Game B, so that Game C is now well defined. We can analyze whether we should play Game C in the long run using the same strategy as before. We are going to analyze whether we are going to win $3 more often than losing $3 when we start with $0. Is that okay? So instead, so here, first of all, so this time we let Q12 to be the probability of winning when our money is not a multiple of 3. And then Q3 to be the probability of winning when our money is the multiple of 3. So we want to construct a Markov chain as before, but this time we use Q12 and Q3. And then this Q12 and Q3 should depend on the coins that we use in game A and game B. Okay, so what is Q12? What is Q3? Okay, so first of all, the chain looks exactly the same, except that this time we are using Q3 rather than P3. We are using Q12 rather than P12 because it is game C, not game B. But then, what are the values of Q12 and Q3? Okay, so Q12, first of all, if Q12 says that, what is the chance of winning $1 if we are not a multiple of 3 and money in our pocket? So because we have 0.5 chance that we are going to play game A, so there is 0.5 chance that we are choosing game A, and then if we are in game A, there is 0.49 chance of winning $1. So this is the portion that we have when we are using the game A. And then for 0.5 chance, we will be choosing game B, and in that case, we can win $1 with 0.74 chance. Okay, so after doing this calculation, we can have a value of Q12. And similarly, for Q3, we have 0.5 times 0.49 plus 0.5 times 0.09. So these are the values that we are using in our particular games. So we have computed what is Q12, we have computed what is Q3, and then the probability of winning $3 before losing, if we start with 0, this is the value that we want to compute here, we are using exactly the same formula as before. So exactly the same formula here, this formula, except that this time, because we are using the same Markov chain, except that we are using Q3 instead of P3, Q12 instead of P12. And now we can simply plug in the value and see what will happen. So after plugging in the value, we will see that the chance of winning is actually greater than 0.5. So actually, game C will be a good choice for us. So we are now, by using a fair coin to decide whether we play game A or game B each round, we are turning 2 bad games into a good game for us. And then what is actually happening? Okay, so actually we are saying that although game A is bad for us in the long run, if we play this alone, but then game A is actually helping us a little bit. So let's look at the chain that we have when we are playing game B. So when we are playing game B, we have, if you look at it, there is, whenever we are at 0, there is much more chance of going back than we move forward. Although, if we move forward after that, it is easy to move further forward. So in such a case, then it is more likely that perhaps we are going to be staying here in this region rather than in this region. So that makes it harder for us to win $3 than before we lose $3. But on the other hand, the purpose of having this game A here is that it shifted the probabilities here a little bit, so that the chance of moving backward when we are at state 0 won't be that bad. It's only 0.71 now. So in that case, it gives us more chance to move forward. And then once we can move forward, it is having more and more chance of moving further forward. Okay, so actually you can imagine a super bad scenario. Suppose that we are playing game B, but now we are changing this coin to be some really strange coin. We are changing the coin here so that there is no chance of moving forward and we must move backward. In such a case, then we can never win $3 before losing $3. But by using game A to help us, we still have non-zero chance of moving forward and then less than 1 chance of moving backward. Then this will give us a way that increases the probability from 0 to non-zero for moving to $3 before losing $3. So that's why the game A here, although it is bad in the long run, it really can help us, okay, by combining this with game B. Okay, this slide, forget about this. This slide says that this is going to be the last class, but it's not the case here for this semester. We will still have the topics about probabilistic method that we will mention in the next 2 weeks. Okay, so but here, so but still, let me thank you for joining this course. And then yeah, this Joyce is a previous tutor, so forget about this. But in any case, okay, we will be doing what? We will be having the exam on week 18, and then we will be releasing assignment 5 this week. So it is again on voluntary purpose. So you can do this and then send your answer to our tutor for checking, and the topic will be about Markov chains. So next week, probabilistic method. Okay, and finally, one thing. Okay, so I just realized that you can fill out the course evaluation starting from the Monday. We have just starting from this Monday. So the course evaluation will be a very, I think, very important thing for me and also for our tutors to improve in our further classes. So if you have a chance, yeah, please help us to fill in the course evaluation. Okay, yeah, that's all for today. And then yeah, and then let me see if you have any question. Okay, if not, then yeah, let's end the class early today, and then you can watch the videos last year for more details. Okay, now, so bye for now, and then see you next week.